Sure. Greetings and welcome, friends. We are talking today again. That's right. It's kind of part two. Talking about solving radical equations, but today I've tacked on like a subtitle to this with two radicals. Radical, dude. Here we go. So I'm just going to jump right into these examples. It's going to be great. So according to our strat from yesterday, I said isolate the radical, square both sides, right? So notice I've got a radical here with a variable, radical here with a variable. This one's already isolated, right? It's on its own on the left-hand side of the equal sign there. So this one's isolated, but this one's not. And if I try to square both sides, it's going to get ugly. So I could isolate this one or bring them both. Either way, these problems get a little ugly, but not very long. So don't worry about it. So let me rewrite this. Square root of x plus 5 is equal to 5 minus the square root of x. So, there we go. So step one, isolate the radical, square both sides. So you pick one of your radicals to isolate and you just roll with it. So I'm going to square both sides here. No matter how scary it is, I'm just going to commit to this. On the left, the square root of x plus 5 all squared is just x plus 5. Right. On the right, I can't distribute a square over addition or subtraction, but you might remember this guy. Yeah, this is our square of a binomial pattern, which becomes a perfect square trinomial is the name of this side of it. So I actually have to use a straight up pattern for this. So a is going to equal 5, b is going to be the square root of x. I'm just going to plug it in for the a's and the b's right there. So, 5 squared minus 2 times 5 times the square root of x plus the square root of x squared. Alright, so, a little bit gross. So let's see, 5 squared is 25 minus 10 square roots of x plus the square root of x squared is x. Alright, and this is equal to x plus 5. Good. Now, notice this looks a little bit uglier than it was originally. However, there's one benefit. This one had 2 radicals in it. This one now only has 1 radical with a variable in it. Aha! So, what am I going to do? I'm going to isolate that radical and square both sides again. So let's bring everything away from the radical. I'll double step this here. So at x minus x, hey, that's 0, x, 0. 5 minus 25 is negative 20. Yep, I don't know what I was thinking a second. I was going to say 30. Equals negative 10 square roots of x. Now, depending on the situation, all right, I could actually choose to square both sides here, and it wouldn't be that bad, because I am allowed to distribute a square over multiplication. Okay, so that is allowed. Or if you want to really get the radical by itself, we can divide both sides by negative 10, which is fine in this case because this is going to be like a non-fraction, so I'm cool with that. So I'm going to get 2 is equal to the square root of x. And now I can square both sides. All right, so to do these problems, it's just a matter of kind of like doing that process twice. And I end up getting x equals 4.
I got 4 equals x.
Yeah, 4 equals x. I did the little flipperoo at the end there because it's nice having the variable on the left side. So let's do a proper check of this. So check. So for the check, I'm going to plug 4 into everywhere there was an x. All right, so that would be the square root of 4 plus 5. Is that equal to 5 minus the square root of 4? Okay, square root of 4 plus 5, that's 9, equals 5 minus 2. The square root of 9 is 3 equals 3. Ha! Behold! So that means this is a legitimate answer to the original equation. Good stuff, right? No es más mal. But yeah, so the idea is isolate one of your radicals, your choice, square both sides, whatever ugliness that brings you through, just commit, all right? And then, right after you do that, then you might have to end up squaring both sides again because you'll end up with one more radical. Let's see, the second example, I'm going to throw it over here because I only got 2 examples today. Should suffice. We'll have plenty of time for some class question. So, here we go. Once again, behold, I've got not just one radical, but 2 with variables in it. Uh-oh. Here we go. So, let's see. I'm going to rewrite it here as well. 3x minus 2 equals 1 plus the square root of the quantity 2x minus 3. So notice one of my radicals is already isolated. All right, that's fine. I mean, I could subtract 1 if I wanted to isolate this guy, but it doesn't matter. It's going to be a little bit ugly either way I take. So let's square both sides. And on the left, it's nice and easy. It's just 3x minus 2. And on the right, this time it's the a plus b pattern, all squared, is equal to a squared plus 2ab plus b squared. So in this case, my a is the 1 and my b is the square root of 2x minus 3, right? So I'm just going to plug those in and just commit, all right? So 1 squared is 1, I'll write the squared, why not? Plus 2 times 1 times the square root of 2x minus 3, plus the square root of 2x minus 3 all squared. All right, so where did I get this? I just directly plugged a's and b's into this pattern. Did I make a mistake? All right, all right. Equals, let's simplify this. 1 plus 2 times the square root of 2x minus 3 plus, square and square root, those guys cancel. So that's 2x minus 3, or plus a 2x minus 3, which is still 2x minus 3. Okay, all right, all right. So even though this whole process has led to me to something a little bit crazier looking, it's actually better because notice there's only one radical here, where here there were 2. All right, so I have made progress. It's kind of like you got to mess up a Rubik's Cube before you can finish solving it, right? Because I always would get one side solved and then I'd be like, I don't want to mess this up, but you got to, right? You're not going to get any other side solved unless you temporarily mess up that one perfect side.
I get one, I guess I'll just get one fix and then I take off the stickers. No.
Actually, to be honest, I've never solved a Rubik's Cube, so to be honest. Although I'm told you can follow an algorithm and it'll work just fine. So let's see, subtract 2x from both sides. Add 3. So I'm going to isolate this other radical here. And hey, we might as well subtract this 1 as well. Lots of stuff going on. I'm leaving this 2 here for the moment. So I'm just doing all my adding and subtracting steps together here. 3x minus...
How would you subtract?
Okay, 3x minus 2x is x. Negative 2 plus 3 is 1. Minus 1 is 0. Oh, so that's just an x over there. Equals 2 times the square root of 2x minus 3.
So do you square it?
Yep. I can actually square both sides, or you can divide by 2. It doesn't matter because I can legally do that. Let's just square both sides. Well, but I have to isolate this, get the radical here. Yeah. So this will be x squared equals, 2 squared is 4, root 2x minus 3 all squared is 2x minus 3. And notice I was super cautious to put parentheses around that because these were being multiplied here and they're going to be multiplied here. I'm going to have to actually distribute this here. So I mean this square root was a grouping symbol, so realize it still is a group after it was squared. So just be aware of that there. X squared equals 8x minus 12. And now solving from here, now I've gotten rid of all my radicals. We're going to actually spend a good couple sections on ways of solving this type of problem. But in general, I'm going to just do a quick breakdown. Step 1, set equal to 0. Step 2, factor. Step 3, set each factor equal to 0. And you've technically seen this in math classes before. And then solve. So this is kind of how to solve a quadratic equation. Specifically by factoring. Not all of them can be solved by factoring, but I believe, I think most of the ones that you come across tonight, or all of them, I'm pretty sure if I recall, are doable this way. So I'm going to set it equal to 0, so I'll bring these all to one side. So I'd have x squared minus 8x plus 12 equals 0. Technically, there are other ways of solving this. You might also remember the quadratic formula, where a is 1, b is negative 8, c is 12. Like I said, we'll cover that in more detail later on in the course. And then, yeah, you could have the quadratic formula, which is x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a, which,
That's what it was.
yeah, you remember it. But let's solve by factoring. So find, let's see, I'm not going to AC method, there's nothing to GCF. I'm going to find the factors of 12 that add to be 8. How about that? So 1 and 12, 2 and 6, 3 and 4.
See,
Oh!
what I would have done is I would have
Yeah, it wouldn't end up working
like,
though.
honest.
The factoring only is beneficial if it's equal to 0 due to this next step that's going to show up. So I'm going to have an x with a 2, an x with a 6 in parentheses. Anyone know what their signs are going to be?
They're going to be both.
The 6 would be positive.
They're the same because they multiply to be positive,
Um,
and they add to be negative,
okay,
So
so,
both.
so minus and minus. And now the benefit of having factored this shows itself because I've got two things that multiply to be 0. All right? And question, what's 2 times 0?
0,
What is 0 times 5?
0,
What is 0 times x?
x,
0.
0, whatever x is. All right, it turns out this is called the zero product property. If you have two things that multiply to be 0, one of them has got to be 0. All right? Because if I said x times y equals 0 as the next thing, one of those had to be 0 in order for that to happen. There's no other way, right, for that to occur. Like 2 times 3 is never going to equal 0, right? One of those numbers has to be 0. So I've got two things that multiply to be 0. So therefore, either x minus 2 equals 0 or x minus 6 equals 0. And I guess I'll write down this property. This is called 0. You don't have to write it down if you don't want. Product property, the ZPP, says if a times b equals 0, then a equals 0 or b equals 0. All right, that's the idea. And that's why that was step 3 right here. I set each factor equal to 0, which is like what I just did there. So let's solve each of those problems. So I'm going to do a plus 2, and over here, hey, why not plus 6, while I'm at it, using that color. X equals 2 or x equals 6. So it appears as though I have two solutions. Wow, what do you know? Friendly friends, behold. But it turns out both of these could be extraneous. One of them could be extraneous, or none of them could be extraneous. And I don't know until you do a check. So let's plug them in.
Wait, does this mean that x could, so you have to do like 4 checks?
No, we won't have that many. We'll only encounter problems that have as many as 2 solutions tonight. So let's see. Let's simplify this. So that's 6 minus 2 over here. 1 plus the square root of 4 minus 3. So that's the square root of 4. Is that equal to 1 plus the square root of 1? Square root of 4 is 2 equals 1 plus 1. That's a true statement, friend. So it sounds like x equals 2 is a good doobie. Let's try the same thing with x equals 6. So square root of 3 times 6 minus 2, is that equal to 1 plus the square root of 2 times 6 minus 3? So that's square root of 18 minus 2, is that equal to 1 plus the square root of 12 minus 3? Square root of 16, is that equal to 1 plus the square root of 9? Is 4 equal to 1 plus 3? Yes!
But could be 1x be 2 and 1x be 6?
It's an or situation in between. So it's committing all of the x's being 2 or all of the x's being 6. I see what you're saying. I got your question now. But yeah, so the general strategy, the new stuff is isolate one of your radicals, square both sides, no matter how ugly it gets, and then you end up with an equation with one radical left, and then you isolate that radical and square both sides, and then you just solve from there. And do a check in case they're extraneous. So thanks for watching, internet friends. Bye-bye.